The Laboratory for Robotics and Intelligent Control Systems, LARICS, is one of the first laboratories founded at the Faculty of Electrical Engineering and Computing at the University of Zagreb.
3 professors and 14 postdocs and PhD students are currently working in the lab. The research in LARICS is focused on control, robotics and intelligence in the areas of flying, walking and driving robots, manipulation, warehousing, as well as collective and automotive systems.
Throughout its 20 years of existence, LARICS has been working on future emerging technologies as well as applied science, closely collaborating with industry. Young researchers have always been the greatest LARICS advantage.
Transportation systems of the future will be safer, faster and more efficient than today. We at LARICS are working on making this future a reality.
Projects EC SafeMobile and Amacal are focused on developing localization, mapping, navigation, and coordination algorithms for autonomous forklifts used within fully automated warehouses. Within the project Exploration Robot for Firefighting Units, we have developed a prototype that can enter dangerous environments and cross obstacle-filled areas. Another area of research includes development of driver assistance torque vectoring algorithms for electric cars with independent drives. In the Adele project, we're working with Ford to extend an existing model of the LNT catalyst. Our goal is to produce a global optimization method in order to improve performance and decrease emissions of poisonous nitrous oxides in the exhaust of diesel engines. Our use of humanoid robots, apart from them being one of our teaching platforms, is mainly aimed towards research in human-robot interaction through a DOOR project. Together with rehabilitation scientists, we're developing a robotic assistant which relies on computer vision, machine learning, and Markov decision processes in order to help clinicians speed up the diagnostics procedure for young children.
Efforts from the LARICS Quadruped Locomotion Research Group are focused on the development of new electrically powered, 4-legged robot research platform and the accompanying control algorithms for ensuring dynamic and robust locomotion. Our emphasis is placed on the utilization of biologically motivated concepts, such as passive, variable passive and active compliance, along with genetic algorithm optimization procedures.
LARICS has been at the forefront of research in aerial robotics since the early days of unmanned aerial vehicles or UAVs. The research in this field involves inventing new technologies of flying that save energy and provide controllability and maneuverability. To be able to fly in windy conditions, we use adaptive control algorithms that optimize the vehicle's reaction to the wind and enable us to, for example, perform inspection of wind turbines in operation, tackling wind gusts and capturing precise snapshots of rotating blades. Used with trajectory planning and localization algorithms, our control systems enable UAVs to fly in narrow corridors, planning trajectories online in real time and avoiding obstacles. We propose a paradigm shift in the way unmanned aerial vehicles are deployed today by bringing them in contact with the environment. These aerial robots have the ability to perform various benchmark manipulation tasks like pick-and-place objects, peg-and-hole assembly, or perching and turning valves. Most quadrotor aerial platforms can be classified as small or micro UAVs. That means they weigh less than 5 kilograms, have a range of less than 10 kilometers with a limited payload and time of flight capabilities. To alleviate this problem, we propose building an internal combustion engine-based UAV capable of carrying up to 50 kilos of payload as well as staying airborne for over an hour.
Except for single robots, our research includes multi-agent systems consisting of tens of units. Our goal is to design the behavior of each unit so that the group as a whole achieves a certain collective behavior.
One of the main questions we want to answer is how to design algorithms for the development of trust among units and to detect faulty or non-cooperative units. We drew our inspiration for biological groups such as flocks, swarms, or human society. In the project Assisi, we're developing a robotic system for researching collective social mechanisms in a biohybrid society of robots and honeybees. In the project Subcultron, we're developing an underwater robotic society for long-term monitoring of the Venice Lagoon with the ability to learn and adapt to environmental changes. Dexterity and compliant motion and perception of robotic manipulators is one of the key issues of industrial manipulators that we strive to explore. For a robot to be truly able to perform human-like manipulation tasks, it needs to be able to perceive the objects in the environment, locate them, and finally manipulate them in a truly compliant way. This drives us to build control algorithms around the concept of force control, allowing the robot to exert a limited amount of force on the object while completing a certain task. Furthermore, it provides the robot with the ability to explore unknown objects and perform delicate operations that require strength and accuracy.
The mission of our lab is to develop close connection and collaborate with leading partners from academia and industry. We also would like to take care that our solutions get approved in the engineering practice satisfying industry needs.
LARICS actively participates in local and international events to raise awareness for science, technology, engineering, and mathematics. We work on multidisciplinary scientific projects where robotics and control help achieve pioneering results.